So, in our last class we have considered supersonic flow past a cone, and we have seen that a source distribution given by f j equal to a j past a cone is given by a source distribution f j equal to a j placed on the axis and we found that for a given cone at given free stream Mach number, this constant A is given by u infinity tan delta by root over cot square delta minus beta square plus tan delta cos hyperbolic inverse cot delta by beta, where we have beta equal to beta square equal to m infinity square minus 1. Delta is the semi vertex angle of the cone. However, and once this source distribution is known, the complete potential and the velocity components and pressure can be computed using the appropriate formulae. Now, this expression for the constant A is little bit unwieldy, and we mentioned that this expression can be simplified if we have a very slender cone. So, for a very slender cone, vertex angle 2 delta is small, and then cot delta is extremely large, and if m infinity is not very large, then cot square delta is cot delta is much larger than beta. Very large, and cot delta is much larger than beta if m infinity is not very large. And in this context, we may again remember that if m infinity is extremely large, the linearized equations themselves are not applicable. So, within the framework of linearized flow theory, this is quite correct. And then this cos hyperbolic cot delta by beta can be approximated cos hyperbolic inverse cot delta by beta is log of 2 by beta delta, and this multiplied by tan delta small, this implies tan delta that is this second term on the denominator is negligible and this then becomes hence the coefficient becomes tan delta by root over cot square delta minus beta and tan delta for small delta is approximated to be delta and cot square delta minus beta square. Since beta square is much less than cot square delta, this can be written as simply cot delta or this becomes tan square delta or delta square. Of course, u infinity is still there. So, this become for a slender cone r by x is usually small and the potential function then becomes the perturbation potential function then becomes pi is minus u infinity delta square into x log 2 x by beta r minus 1. This is obtained from the general expression obtained from the relation which we evaluated in the last class, that phi x r is minus a x cos hyperbolic inverse x by beta r minus 1 minus beta r by x square. So, simplification of this expression gives with a equal to minus u infinity delta square gives this expression for phi for a slender cone. Similarly, the velocity components can also be this u by u infinity and v by u infinity, they become on the cone surface minus delta square log 2 by beta delta and v by u infinity surface is delta. In this we have the pressure coefficient then becomes minus 2 u by u infinity minus v by u infinity square equal to 2 delta square log of 2 by beta delta minus half. Now, for this cylinder cone, the equivalent two dimensional body is a cylinder wedge, and we have earlier seen that for cylinder wedge you remember 2 by root over m infinity square minus 1 into theta, or theta is the semi vertex angle, which you have denoted here by delta. So, it is 2 delta by beta. So, if we compare these two relations, what we see is that pressure rise on the cone surface is much less. Is much less when you compare it to a wedge. Eventually, if we distance along the axis, for wedge the pressure distribution is the pressure on the wedge surface is constant, while for cone this becomes so the pressure rise on the cone surface is much gentle and so this is once again a 3 dimensional relieving effect. That is when in case of a 3 dimensional body, that is as a cone, the flow has an additional direction to adjust itself, while in 2 dimensional case there is no such extra direction, because in the spanwise direction the conditions are same at all stations. That is what the meaning of 2 dimensional flow. As a consequence, in 2 dimensional flow the flow has not that additional direction available to it for adjusting, while in case of a 3 dimensional object there is an additional direction available in which the flow can adjust itself, and consequently the effect of the body is much less on the flow and the pressure on this body is much less. Knowing the pressure distribution and full potential on the surface, we can compute the forces that are acting on the body, in this case the cone, or in general any body of revolution in axial symmetric flow. This is obvious that in case of axially symmetric flow, there will be no lift force, because the pressure on the upper half of the body and the lower half of the body will cancel each other. However, a drag force will act, which we have already mentioned as the wave drag. So, that drag will be present. However, before we try to compute that forces acting on this body of revolution in axially symmetric flow, we will try to see what happens if the flow is not axially symmetric. So, we will now consider non-axisymmetric flow. Over a body of bodies of revolution. Let us consider again a body of revolution. There is the axial axis x and the normal axis z. And let us say that the free stream is not along the axis, but aligned at an angle of attack. We call this u infinity, and the angle of attack is, we will call it so, free stream at an angle alpha of course, corresponding to Mach number m infinity at angle of attack alpha. Now, free stream has two components of free stream. The axial component u a is u infinity cos alpha, and the cross flow component Now, since we are dealing with linearized flow, which allows superposition, we can think this flow to be a superposition of two separate flow, one axial flow with free stream speed of u a and another cross flow with free stream speed of u c. So, the problem is linear problem allows superposition which allows the flow is total flow is superposition of axial flow plus cross flow. So, the solution at the solution for this problem, which is the solution which is the perturbation potential as a function of x or theta, is sum of two potential. One is the axial flow solution phi a x r plus phi c x r theta. Now, the axial flow solution we have already discussed how to obtain the axial flow solution. Now, this axial problem, if we want to solve this axial problem separately, it is essentially required that our boundary condition can also be splitted in axial and cross flow component part. So, phi a can be obtained as before if boundary condition can be split in axial and cross flow part. Anyway, we will see that this boundary condition can also be split in axial and cross flow part. However, at this stage we will just assume that the boundary condition can really be split and we can get a separate solution for phi a and can obtain the solution by the method that we have discussed earlier. Now, one thing in this case must remember that while solving the problem for axial and cross flow, the corresponding Mach number in the potential flow equation must be taken as m infinity, that is undivided Mach number, not the Mach number based on the component. So, for this solve for phi a and phi c, the Mach number in the equation must be m infinity corresponding to u infinity, not m corresponding to u a and u c. That is, while solving, the velocity should be taken as u a or u c, but the Mach number must be taken as m infinity. That is because the flow is the nature of the flow and the entire flow is governed by that m infinity corresponding to the free stream Mach number, not by the part Mach number. Anyway, let us see that we have the axial flow solution, then we have phi a known. Now, phi c must satisfy the cross flow equation or the full equation d 2 phi c d r square plus 1 by r d phi c d r plus 1 by r square d 2 phi c d theta square minus beta square equal to d 2 phi c d x square 0 and beta square is m infinity square minus 1. That is, in this, even though the system speed is u c, the Mach number is not corresponding to that u c, but corresponding to m infinity. So, this phi c must satisfy this equation. One thing in this case must be remember that this supersonic flow equation is valid even if the component u c is subsonic, provided m infinity is supersonic. So, as long as the main flow is supersonic or the total flow is supersonic, if the cross flow component is subsonic, still the equation for supersonic flow is to be taken. And once again, since in this case we have split the problem in two parts, the axial and cross flow part. In case if it happens that the perturbations corresponding to axial flow or cross flow is large, is symmetrical, as long as the total perturbation is small. So, the small perturbation theory may still hold if the cross flow perturbations are not large, provided the total perturbation, that is cross flow perturbation plus axial flow perturbation, remains small. Now, the axial flow satisfies the governing equation corresponding to d 2 phi a d r square plus 1 by r d phi a d r minus beta square d 2 phi a d x square equal to 0. The axial flow is solution of this equation. Now, if we differentiate this equation with respect to r, the resulting equation will also be satisfied by phi a. So, phi a also satisfies, if we differentiate this equation with respect to r, the resulting equation is also satisfied by phi a. So, phi a satisfies since phi satisfies this equation, phi also satisfies this equation, which is obtained just by differentiating this with respect to r. Now, if this d phi a d r present in this equation is replaced by cos theta d phi a dr, then that is also phi also satisfies that equation. That means, if we introduce another cos theta here, phi also satisfies that, because that introduction of phi cos theta in this equation does not alter anything, which is constant for this particular equation. There is no theta derivative being present in the equation. So, this implies phi a also satisfies d phi a dr plus 1 by r d dr of cos theta d phi dr minus sorry, in this equation these are not square, this is first derivative. So, minus cos theta by r square d phi a dr minus beta square d 2 dx 2 cos theta d phi a dr equal to 0. Or for this equation cos theta d phi a dr is a solution. Now, this equation can also be written as, or we can write this term as cos theta d phi a dr plus 1 by r d dr of cos theta d phi a dr. Now, in this this term we can write as 1 by r square d 2 d theta square cos theta d phi a dr minus beta square d 2 dx 2 cos theta d phi a dr equal to 0. Now, if we look to this equation, this is exactly the equation for the cross flow equation. So, comparing it with the cross flow equation, what we get is that phi c equal to cos theta d phi a dr. So, what we see that if we have the axial flow solution phi a known, then this cos theta d phi a dr satisfies the cross flow equation, or the cross flow solution is cos theta d phi a dr. Or we can write phi c as a solution of x or theta is cos theta d phi a dr, which is of course a function of x and r alone phi a, or this can also be written as d phi a dz. So, it shows clearly that if we have the axial flow solution known, we can straightaway obtain the cross flow solution without properly solving the equation. Now, to obtain that, let us see what is d phi a dr. d phi a dr is 1 by r. We have already the expression for phi or phi a 0 to x minus beta r f prime xi x minus xi into d xi. This can be written by integration by parts as minus beta square r 0 to x minus beta r f xi d xi by root over by x minus xi square minus beta square r square to the power 3 by 2 plus 1 by r f xi x minus xi by So, this is integration by parts. Now, looking to the second term becomes 0 if the body is pointed when the lower limit is 0. So, looking to the second term at the lower limit becomes 0 if f xi equal to 0, which we know for pointed body. And at the upper limit, this it becomes infinite. At the upper limit, this term becomes infinite. So, it is rule of integration to consider only the finite part of the first integral. So, what we need is only the finite part or called the principal part first term is taken. And this is formally written as minus beta square r into and the finite part of this integral. And this symbol represents the principal part of the integral. Now, this undetermined part, this f xi or f prime xi in whichever form we use for this can be obtained by satisfying the boundary conditions. So, so finally, the cross flow solution we can write as phi phi c x r theta equal to cos theta into d phi a dr, and d phi a dr we have two forms. So, taking this first form becomes cos theta by r into 0 to x minus beta r f prime xi x minus xi by root over x minus xi square minus beta square r square d xi, or x minus y square minus beta square r square to the power 3 by 2 the finite part of it. So, as a cross flow solution we can use any of these to find the cross flow potential, provided we know the strength of the singularities f xi or f prime xi. Now, we mentioned that this solution, that is the solution of axial part and cross flow part separately, can be carried out if the boundary condition can be split into two parts separately. That is, the boundary condition can also be split in axial and compressible cross flow part, and this is what now we like to see. To check if boundary condition can be split. Now, we have say radial velocity at any cross section is the undisturbed stream u c cos theta plus a perturbation part d phi dr. Similarly, the axial velocity again at any cross section is u a plus d phi dx. Now, the boundary condition is the tangential component need not be checked, because the tangential component always satisfies the boundary condition, which we have mentioned earlier, that only the meridional section should be looked into. The boundary condition, what we had is dr dx equal to v by u infinity plus u. Is the body contour. Now, in this we substitute this, and this gives us u c cos theta plus d phi dr on the body is dr dx into u a plus d phi where this is what is this axial total axial velocity. Now, we will substitute phi as phi a plus phi c in this expression, and hence this becomes d phi a dr plus d phi c dr plus u c cos theta equal to dr dx into u a plus now see from here that we can very easily split it this taking all the axial term in this equation, sorry d we have d phi a dr of course from the body is dr dx into u a plus see that this contains only phi a, that is only the axial flow. So, this is for the axial flow. And the remaining term now for a slender body this dr dx is small and d phi c dx is also small and consequently they can be the product can be neglected. Since this product is lower order, it can be neglected with in comparison to this term, and consequently this can be taken as this. So, looking to what we have done today, first of all we approximated or simplified the source expression for the source distribution when the cone is very slender for the general from the more accurate solution that we obtained in the last class. Further then we went on to see the asymmetric flow or the when the flow is non-axisymmetric with respect to the body, that is the flow is at an angle of attack. We saw that being the problem being linearized, it offers us a possibility to split the flow in two separate parts, one being the axial flow component and the other is the cross flow component, and provided that the boundary condition can also be splitted in these two parts, which we saw that can be done, that the boundary condition can be splitted. And since the boundary condition can be splitted, the flow can be solved as a combination of two separate flow, an axial flow and a cross flow. And also we saw that the once the axial flow solution is known, the cross flow solution can be straightaway obtained by a very simple relationship which gives that the cross flow part of the potential phi c as a function of x, r and theta is simply the product of the axial flow potential phi a and derivative of the axial flow potential phi a multiplied by cosine of theta, that is phi c is simply cos theta d phi a d r. And then we saw that since phi a is known, or the general solution for phi a is known when which is simply a source distribution along the axis, and whose strength can be obtained from the satisfaction of the boundary condition. And then once the axial flow solution phi a is known, the cross flow solution can straightaway be obtained by cos theta into d phi a d r, which we saw that can be expressed in two different form. One containing f prime xi as the singularity strength, the other containing the singularity strength as f xi, but which is having a r cube function on the denominator or equivalent to an r cube function in the denominator, and in this case only the finite part or the principal part of the integration should be taken. And with this we can now extend our cross flow solution over a cylinder cone to a cross flow solution over the cone and complete the conical flow solution for any arbitrary flow, of course, within the framework of linearized small perturbation theory, and we can compute the forces. So, next we will compute the forces that acts on a body either at axial symmetric flow or asymmetric flow.